Welcome everyone. In this video I'm going to show you a displacement sensor again. This is another version of a displacement sensor. So already I have shown you some very simple, which is based on a caliper, for example, a digital caliper or a digital readout, and I used something which is based on a linear potentiometer, a slide potentiometer. And in this case I'm using another type of displacement sensor, which is here, you can see. It's basically, we have a cylinder and there is a piston or rod which is moving in and out. The stroke length of this particular piece is 25 millimeters, so I can come out a bit more than 25 millimeters. And yeah, so if I'm correct, then this works in the following way. So you move this rod in and out. So at the end of this rod, so somewhere here inside the cylinder, there is a wheel. And then what that wheel does is basically there is a wedge-shaped plate or a metal piece, and then my index finger here is the wheel. And then if you move in and out, you increase or decrease the distance between the two wedges. So basically you bend these wedges somewhat. And what happens is that if you put a strain gauge on one of these wedges or on both sides of these plates or pieces of metal, then you can measure the deflection of this wedge which is inside this. So as you move out, the wedges go closer to each other because you remove the wheel, or if you move it inside, then the wedges like separate. So this scissor type of opening is opening up because you push inside the wheel. So you bend it. So the deflection is changing of this metal part, and you can read this deflection with a strain gauge, and since it's a elastic deformation of those metal parts, then this should be linear. So basically you can like linearly bend some type of metal inside this cylinder and then transform that into resistance, or change in the resistance, which is the resistance of the strain gauge. So if you apply some current or voltage on this resistor or resistance, then you can change the output voltage of this circuit. So basically this is a resistance-based circuit, and in fact the output is according to that. So I don't want to disassemble here, but what we have, so we have this cylinder, and then there are basically 4 cables. One is the shielding, so this black is here. And then we have 3 other cables. 2 is basically the output and the ground. And the 4th is the power supply or the voltage for this. So we change the distance of this piston, and then we change the output voltage of this basically a potentiometer, and we read it with a 16-bit AD converter, and then we send it to an Arduino, and that goes to the computer. And I also print it on a LCD to make it more spectacular. And some details about this. So this is called like KPM12-J. The 12 refers to the diameter of this cylinder. And this, as I said, this particular piece can open up 25 millimeters plus a little bit more. And one thing that we also have to know, that if you start to open this, then the voltage is not changing until a certain distance, because there is like a sort of buffer area. So you have to open this cylinder a little bit, and then you can start to measure. So basically, if the piston or this nut is touching the cylinder, then that's the 0 position. but in reality the real zero position where the output voltage starts to change is somewhere like +4 or 3 millimeters, and then you can go the 25 millimeters outside. And this should be rather precise. So the datasheet says that the mechanical precision of this, or the repeatability of this piston, is basically 10 micrometers. So if you move out and back and to the same spot, then you are ending up with like ±10 microns of precision. And the precision which comes from the resistance of this thing is even better. That's like 0.1%. So in the case of this 25 millimeter stroke length device, is basically 2.5 micrometers. And that's pretty good. So this can be used for projects which require something which is small. In fact, the cylinder itself is like 9.5 centimeters long, and then the distance between the two holes here is like 13 centimeters roughly. So yeah, this is quite good for reading precise data and precise displacements. So you can use this for robots or something which does repetitive motions, and so on and so on. So now I will demonstrate you some very simple stuff, which I basically do. I just switch on the logging of the data. So the displacement will be shown on this LCD here. And now I print the displacement at every 200 milliseconds. So it's a rather slow refreshing rate of the data. So now I start it. So now you can see that it is changing. So because we are at the zero position, which is technically not the zero, but I calibrated it like this. So the voltage, which is read by the AD converter, is equivalent of the 2.3 millimeter. That's the absolute position. So now I calibrated this in a way that it is always showing the absolute position of the piston, or like how much I opened this. So now I just open it a little bit, and now we are at 13.98 something millimeters. And as you can see, I just put it down so I don't touch anything, that the first two digits are basically unchanged, but then the third digit is jumping. So basically we can have a precise data as the data sheet suggests. So this is like 100 micrometers, I mean order of magnitude, and then 10 micrometers order of magnitude, and then this is the micrometer order of magnitude, the third digit here, because we are reading millimeters. So then it's pretty good that we can read something within like 10 micrometers precision. So if I change this, then it of course immediately reacts. And then I open this to the maximum, so you can see that it's 27, so it's a bit over 25, but that is because there is a dead spot between 0 and 2 point something millimeters, so the ball scale is shifted by 2 or 3 millimeters. So this is like that 25, which is the full range, plus that dead spot or dead range in the beginning. So I close it a little bit and I don't touch it. So you can see that, again, the first two digits are pretty stable, and then the third digit is jumping up and down. So you can see. So this is a very good displacement sensor because it's rather precise. So you can use it for a lot of stuff where you require some sort of precision. And I'm pretty sure that I can even get rid of all of these strange wires and I get a bit better precision. I can further increase the precision by changing the settings of the AD converter. Now it's on the worst resolution. So if I increase the resolution, so I change the PGA settings, then I'm pretty sure that I can increase the precision of the numbers. So maybe I can make the third digit precise as well. But yeah, if you can see, it's changing within a small range, so it's not that bad. So basically this is the setup. I will now go to the computer and quickly show you the code. So we are here with the code now. So let's start with the libraries. So we had the library for the I2C communication for the LCD, and then we had this wire, which is also needed to realize the communication. We add the library for the AD converter for that board, and then we initialize or define this liquid crystal I2C stuff. So basically we have these 16 characters and 2 lines LCD, and then we do the same with the AD converter. Then we define our variables. We need one variable for storing the values of the serial input. So whatever we send to the Arduino is getting stored in this variable. And then we have the same sampling frequency, which is basically the frequency of the serial.print. So what is the time between 2 prints basically. Then we need some variable for the distance. This distance is basically the absolute position of the piston. I calibrated it just roughly. And ADC read is basically the bits which are coming from the AD converter. And then we move on to the setup here. So we just start with this baud rate, and then we print something which is basically some information. So I connect the board to the computer, and then I can see what software is currently running on the board. And then this is just some useful information about the settings of the gain. So you can read this and you can decide which kind of gain you use. For this particular project I'm using the largest gain because my maximum voltage is 5 volts, which is the 5 volt output of the Arduino board. But if you decide to use smaller voltages, then you can move down with the PGA setting, and that gives you better resolution, because what you do here by changing the gain is basically, if you use this 2/3, that means that the total range of your voltage is more than 12 volts. So you divide the 12 volts with the resolution, which is 2 to the 16th power value. So you divide the total range of the voltage with that number. But if you decrease the range, now we have like 8 volts, so you divide 8 with the 2 to the 16th power, so then you have more finer steps between the voltages. And as you can see here, the voltages or the steps in the voltages are written. So here, if you use the 2/3 gain, then 0.18 millivolts. This is already small because this is the fraction of millivolt, but still. And then if you further go down, then you can have like even nanovolts of step size or resolution, but then you use a very large gain and you are restricted to very small range of voltage. So now for this particular project we use the largest, and we have this ads.set_SPS, which is basically the sampling speed. I just used some random value which is relatively fast. You can change this. I will tell you how. And then, yeah, we set up the gain, and then we start the ADS. And then we take care of the LCD. So basically we have to initialize it, we turn on the backlight, and then we clear it. So if something was on the screen, we get rid of it. We put the cursor on the first place, or into the place of the first character in the first line. So this is the 0, 0, because we start from 0, and then we print something there. And then we move the cursor one line down, so we print in the second line, and then we print something, and then we just wait, and we don't clean it. This message, this KPM12 something, and the reading display will be shown on the screen as long as you don't change it. And then we move into the loop. So I made it very simple because this is just a very short code. So we start a timer, or basically we store the current time of the Arduino in this start time variable. So later on we can use this for measuring running time, for example. So then we say that if the serial is available, then we read a character from the serial port, because we will use characters to enter into different stages of this switch case, and then based on the character we can read or change the sampling rate, and so on and so on. So we read the data, and then we check what was the character. So we see that, okay, for example, it can be a D. We wait a little bit, and we wait for another set of characters, which now is basically will be a number, an integer. And then we give that number to this SPS if checker. So what this does is basically we change the SPS setting by reading a number, and we give that number to this function, and based on that we can change the SPS. And we can do the same with the PGA. So if I send W and a number following this single letter, then we can change the PGA setting based on the number that we send. I will show you later how. And then we send the S, which is basically a simple start command, let's say. And then while we don't send a capital N to the Arduino through the serial code, then we just basically repeat this stuff here, the printing. So we start the timer again, so we can measure the elapsed time, and then we read the AD converter by reading the 0 and the first pins, so the A0 and A1 pins, so in a differential mode. And then we calculate the distance or the position of the piston based on the calibration, which I did. And then we print it. So first elapsed time, and we put a tabulation, and then the raw data and another tab, and then the distance with 6 digits of precision. And then we wait for 200 milliseconds, and we repeat it again until we don't send a capital N. If we send an R, this is a single readout, so it does the same as previously, but just once. So you will get back one number, and that's all. And we don't read time because of this, because we don't need time. And we wait 3 seconds, and that's all. It exits this case, and then it will wait for a new command. And then we use the LCD, so we send a small L, and we also wait for a sampling frequency, which can be, for example, 200, which means that the sampling frequency will be 200 milliseconds. So at every 200 milliseconds we will print something on the serial port and the LCD. So the same, we start the timer, we read the AD converter in differential mode, we calculate the distance or the position of the piston, and then this is based on a calibration, and then we print everything on the serial port, and then we print everything on the LCD screen as well, and we weight according to the sampling frequency basically. So this is all what makes it work. And then we have like two other functions, which is basically, one is the PGA setting. So if we try to change the PGA, then we have to send a number, and based on the number, so we check these numbers with an else if statement, we can set different gain values. So that's all. You can read it, and it's quite easy to understand. And we do the same with the sampling frequency. So we read a number, a simple integer, and based on the value of the integer, we can check these things. And yeah, I put this here because maybe you can use like the value itself. So we can check if the value is exactly 1, then we change the SPS to this, and so on and so on. And these numbers like 128, 250 and so on, these are all defined in this library. So if you want to understand why are these commands are used, for example these here, or why are these SPS values are like this, so 920, why it is 920, then you just check this library and you can like trace back everything. So yeah, I don't want to waste more time to really go into details, but I think you can understand everything based on these pieces of the code. So I hope it was helpful, and I hope you learned something. So I will upload the whole code, so you don't need to struggle with typing it. But one thing that you have to change is this. So if you have something else which is used to measure the displacement, you have to do the calibration yourself. And basically what you do, these devices are usually linear. So what you do here is you measure one displacement with a ruler or a caliper or a screw micrometer or something, and then you read the bit. So there will be a value of the bit read from the AD converter, which corresponds to a distance of the piston. And then you open the piston more, and then there will be a different bit. And you repeat this like 10 times or even more, the more the better, and then you fit a linear function on this, and based on the linear function you have the equation of this line. So basically this is the A, and then this is the X, and this is the B from that equation, and you just copy paste the numbers, and that's all. So it's very simple. But yeah, if you have any questions or if you need help with these kind of things, just let me know. So see you in the next video.